What if the end of the dinosaurs wasn't just a random event, but a dramatic, fiery apocalypse triggered by forces from beyond our world? How did a single moment change the course of life on Earth forever? Stay with us as we reveal the incredible story of the dinosaurs' extinction, driven by an asteroid impact so powerful it left a mark still visible today. This tale isn't just about the past, it's a stark reminder of the potential dangers lurking in space. Curious about how it all unfolded, let's uncover the astonishing events that reshaped our planet. The extinction of the dinosaurs is one of the most intriguing and significant events in Earth's history. Occurring approximately 66 million years ago, this mass extinction event marked the end of the Cretaceous period and led to the rise of mammals and eventually humans. Among various theories proposed by scientists, the asteroid impact hypothesis is the most widely accepted explanation for this dramatic event. This theory gained substantial support through the discovery of a massive crater known as the Chicxulub crater, located on the Yucatan Peninsula in Mexico. Measuring about 150 kilometers in diameter, this crater indicates the impact of a colossal asteroid or comet, estimated to be around 10 to 15 kilometers wide. The energy released by this collision was equivalent to billions of atomic bombs, creating catastrophic effects on a global scale. The initial impact would have generated an immense shockwave, triggering massive earthquakes and volcanic eruptions worldwide. The immediate vicinity of the impact site would have been incinerated, while colossal tsunamis swept across oceans, devastating coastal regions. Furthermore, the collision propelled vast amounts of debris, including vaporized rock and molten material, into the atmosphere. The debris and soot from widespread wildfires caused by the impact likely led to a dramatic cooling of the Earth's surface. This impact winter scenario, characterized by prolonged darkness and plummeting temperatures, disrupted photosynthesis, leading to the collapse of food chains. The subsequent acid rain and climatic changes further contributed to the inhospitable conditions, making it difficult for many species to survive. By understanding the asteroid impact hypothesis, we gain insight into the fragility of life on Earth and the potential consequences of extraterrestrial threats. The extinction of the dinosaurs serves as a stark reminder of the dynamic and often violent nature of our planet's history, shaping the evolution of life in profound ways. The impact event that led to the extinction of the dinosaurs is one of the most significant occurrences in Earth's history. This cataclysmic event took place approximately 66 million years ago, when a massive asteroid, estimated to be about 10 to 15 kilometers in diameter, collided with Earth. This asteroid struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater, a monumental geological scar that measures around 150 kilometers in diameter. The force of the impact was unimaginably powerful, releasing energy equivalent to billions of atomic bombs. The initial collision generated a shockwave that traveled across the planet, causing severe earthquakes and volcanic eruptions. The immediate vicinity of the impact site was instantly vaporized, and the tremendous heat produced caused widespread wildfires, incinerating vast areas of vegetation and wildlife. One of the most catastrophic consequences of the impact was the generation of enormous tsunamis. These towering waves swept across the oceans, inundating coastal regions and causing further devastation. The impact also ejected an immense amount of debris, including vaporized rock and molten material, into the atmosphere. This debris, combined with soot from the wildfires, formed a dense cloud that enveloped the Earth. This cloud of particles blocked sunlight, leading to a significant drop in global temperatures. This phenomenon, known as an impact winter, resulted in prolonged darkness and cooler temperatures that disrupted the Earth's climate. Photosynthesis was severely inhibited, leading to the collapse of food chains, both on land and in the oceans. Many species, unable to adapt to the rapidly changing environment, perished. The impact event also caused the release of sulfuric acid aerosols into the atmosphere, leading to acid rain that further harmed the environment. The combination of darkness, cold, and acid rain created inhospitable conditions for life, contributing to the mass extinction that wiped out approximately 75% of Earth's species, including all non-avian dinosaurs. This event marked a pivotal point in Earth's history, paving the way for the rise of mammals and the eventual dominance of humans. The Chicxulub crater, located on the Yucatan Peninsula in Mexico, is the most compelling evidence supporting the asteroid impact hypothesis for the extinction of the dinosaurs. This massive crater, buried under layers of sediment and partially submerged offshore, measures approximately 150 kilometers in diameter and was formed around 66 million years ago by a colossal asteroid impact. The discovery of the Chicxulub crater in the late 20th century revolutionized our understanding of the Cretaceous-Paleogene (KPG) extinction event. Geologists identified the crater through a combination of geophysical surveys, drilling projects, and the analysis of shocked quartz and tektite small, glassy particles formed by the intense heat and pressure, the impact. These findings provided irrefutable evidence of a massive extraterrestrial collision. The impact at Chicxulub released an unimaginable amount of energy, estimated to be equivalent to billions of atomic bombs. This cataclysmic explosion vaporized the asteroid and a significant portion of the Earth's crust, ejecting enormous quantities of debris into the atmosphere. The force of the impact created a central peak ring within the crater, a characteristic feature of large impact craters, and caused massive tsunamis that spread across the oceans. The debris from the impact, including dust, ash, and sulfur aerosols, was thrown high into the atmosphere, forming a global cloud that blocks sunlight. This led to a dramatic cooling of the Earth's surface, known as an impact winter. The lack of sunlight caused photosynthesis to halt, leading to the collapse of food chains and triggering the mass extinction of numerous species, including the non-avian dinosaurs. Furthermore, the impact released vast quantities of carbon dioxide and sulfur dioxide, contributing to acid rain that further devastated the environment. The Chicxulub impactor's explosive force, coupled with the global climatic changes it triggered, created a domino effect of environmental catastrophes that rendered the planet inhospitable for many forms of life. The immediate aftermath of the asteroid impact that created the Chicxulub crater was a period of intense and widespread devastation. The collision, occurring approximately 66 million years ago, set off a chain reaction of catastrophic events that reshaped the Earth's environment and led to the mass extinction of the dinosaurs. The initial impact generated an intense shock wave that traveled at supersonic speeds, causing violent earthquakes and volcanic eruptions around the globe. The energy released by the collision was equivalent to billions of atomic bombs, instantly vaporizing the asteroid and a significant portion of the Earth's crust at the impact site. The immediate vicinity of the Chicxulub crater was subjected to temperatures hotter than the surface of the Sun, causing incineration of all life forms and vegetation. One of the most immediate consequences was the formation of gigantic tsunamis. These tsunamis, some reaching heights of several hundred meters, radiated outwards from the impact site, inundating coastal areas and causing widespread destruction. The force of these waves was powerful enough to erode coastlines and transport massive amounts of debris far inland. Simultaneously, the impact ejected vast quantities of debris, including vaporized rock and molten material, high into the atmosphere. This debris, along with the soot from widespread wildfires, ignited by the impact's thermal radiation, formed a dense cloud that encircled the Earth. The skies darkened as this cloud blocked sunlight, leading to an immediate drop in temperatures. This phenomenon known as an impact winter, caused a dramatic and rapid cooling of the Earth's surface. The sudden darkness and temperature drop disrupted photosynthesis, leading to a collapse of the food chain. Plants and phytoplankton, the primary producers in both terrestrial and marine ecosystems, began to die off, causing herbivores and subsequently carnivores to starve. In addition to the cooling, the impact released large amounts of sulfur dioxide into the atmosphere, leading to acid rain. This acidic precipitation further damaged plant life and altered the chemistry of oceans and freshwater systems, contributing to the inhospitable conditions that persisted in the aftermath of the impact. The immediate aftermath of the Chicxulub impact was a period of rapid environmental change and mass destruction. These initial events set the stage for the longer-term climatic shifts and ecological upheavals that ultimately led to the extinction of approximately 75% of Earth species, including all non-avian dinosaurs. The asteroid impact that created the Chicxulub crater not only caused immediate destruction, but also ignited global wildfires, contributing significantly to the mass extinction event 66 million years ago. The energy released by the collision was immense, and the heat generated was enough to ignite vegetation over vast areas, leading to widespread fires. Upon impact, the asteroid vaporized and created a fireball that incinerated everything in its vicinity. The intense thermal radiation from the explosion ignited wildfires that spread rapidly across continents. This process was further fueled by the enormous quantities of debris and superheated rock ejected into the atmosphere, which then re-entered the Earth's atmosphere at high speeds, causing additional fires upon landing. These global wildfires released massive amounts of carbon dioxide, methane, and other greenhouse gases into the atmosphere. The immediate effect was a rapid increase in atmospheric temperatures, exacerbating the initial devastation caused by the impact. Additionally, the fires produced vast amounts of soot and ash, which were lofted into the stratosphere and contributed to the formation of a dense cloud that blocked sunlight. The combination of soot and other particulates in the atmosphere resulted in a phenomenon known as impact winter. This period of darkness and cooling severely disrupted photosynthesis, leading to the collapse of food chains. The lack of sunlight and the reduction in global temperatures caused a dramatic decline in plant life, which directly affected herbivorous dinosaurs and subsequently the carnivores that preyed on them. Furthermore, the wildfires had a profound impact on the planet's biosphere. The combustion of vast amounts of organic material released toxic compounds into the atmosphere, leading to acid rain that further damaged ecosystems. The acid rain affected both terrestrial and aquatic environments, altering soil and water chemistry and making survival even more challenging for many species. The scale and intensity of these wildfires were unprecedented. Charcoal deposits found in geological layers around the world serve as evidence of the widespread nature of these fires. These deposits indicate that the fires were not localized, but rather a global phenomenon, affecting nearly every continent. The asteroid impact that created the Chicxulub crater generated colossal tsunamis, which were among the most immediate and devastating consequences of the collision. These tsunamis played a significant role in the mass extinction event by causing widespread destruction to coastal ecosystems and contributing to the overall environmental upheaval. When the asteroid struck the shallow waters off the Yucatan Peninsula, it displaced an enormous volume of water, generating a series of massive waves. These waves radiated outward from the impact site at incredible speeds, reaching heights estimated to be over 100 meters, 328 feet, near the source and retaining substantial energy as they traveled across the oceans. The initial waves would have inundated coastal regions within minutes to hours, causing widespread destruction. Coastal landscapes were drastically altered as the waves eroded shorelines, swept away vegetation, and demolished habitats. The force of the water uprooted trees, destroyed animal burrows, and left large areas barren. Marine life was particularly vulnerable, with many organisms being swept away or stranded far from their original habitats. Evidence of these tsunamis has been found in geological records around the world. Sediment deposits containing mixed materials from both marine and terrestrial environments indicate the immense force and reach of these waves. These deposits, known as tsunamiites, have been discovered in various locations, including North America, South America, and even as far away as New Zealand, highlighting the global impact of the Chicxulub-induced tsunamis. The tsunamis also contributed to the redistribution of sediments and the formation of new geological features. For example, large boulders and marine sediments were transported inland and deposited in unusual locations, providing a physical record of the catastrophic event. These deposits have been studied extensively by geologists to understand the scale and impact of the tsunamis. In addition to the immediate physical destruction, the tsunamis had long-term ecological consequences. Coastal ecosystems, including mangroves, coral reefs, and estuaries, were severely damaged. These ecosystems are critical for supporting a diverse array of species, and their destruction led to a significant loss of biodiversity. The disruption of these habitats had a cascading effect on the food web, impacting species that relied on these environments for food and shelter. Furthermore, the tsunamis would have contributed to the dispersal of pollutants and debris. The waves carried contaminants, including heavy metals and organic pollutants from the impact sites, spreading them across vast areas. This further exacerbated the environmental stress caused by the impact and contributed to the inhospitable conditions that followed. The asteroid impact that created the Chicxulub crater also triggered a series of environmental disasters, including the generation of acid rain, which had devastating effects on the planet's ecosystems. This phenomenon played a significant role in the mass extinction event by altering the chemistry of the atmosphere, soil, and water, further contributing to the collapse of the biosphere. The impact released an enormous amount of energy, vaporizing the asteroid and a significant portion of the Earth's crust. This vaporization released a vast quantity of sulfur-rich rocks into the atmosphere. When these sulfur compounds combined with water vapor, they formed sulfuric acid aerosols. These aerosols were then distributed globally by atmospheric circulation, leading to widespread acid rain. The acid rain had several immediate and long-term effects on the environment. The most direct impact was on terrestrial vegetation. The acid rain severely damaged plant tissues, inhibiting photosynthesis and leading to widespread deforestation. This loss of vegetation had a cascading effect on the entire food chain, as herbivorous dinosaurs and other plant-eating organisms found their food sources drastically reduced. Consequently, the carnivores that depended on these herbivores also faced starvation. In aquatic environments, the acid rain caused a rapid drop in the pH of oceans, rivers, and lakes. This acidification had lethal effects on many marine species, particularly those with calcium carbonate shells or skeletons, such as mollusks, corals, and certain types of plankton. These organisms experienced difficulty in maintaining their calcium carbonate structures in the more acidic conditions, leading to a decline in their populations. The collapse of these primary producers and key species further disrupted marine food webs. The acid rain also led to soil acidification, which altered the availability of essential nutrients and minerals. This change in soil chemistry affected plant growth and further compounded the challenges faced by terrestrial ecosystems. Additionally, acidified soils leached toxic metals like aluminum, which can be harmful to both plant and animal life. Evidence of acid rain following the Chicxulub impact is supported by the presence of certain geochemical markers in sediment layers from that period. Elevated levels of sulfur, and other trace elements in these layers indicate the widespread deposition of acid rain and its impact on the environment. The asteroid impact that formed the Chicxulub crater 66 million years ago also created a prolonged period of atmospheric dust and darkness, significantly contributing to the mass extinction event. This phenomenon, often referred to as impact winter, had drastic effects on the Earth's climate and ecosystems, playing a critical role in the extinction of the dinosaurs and many other species. When the asteroid struck the Earth, it vaporized a massive amount of rock and debris, propelling it high into the atmosphere. This ejected material included fine dust particles, soot from widespread wildfires, and other aerosols. The force of the impact was so great that it launched this debris into the stratosphere, where it spread around the globe, forming a dense cloud that blocked sunlight. The immediate consequence of this global dust cloud was a dramatic reduction in sunlight reaching the Earth's surface. This led to a significant drop in temperatures, a condition known as impact winter. The reduction in sunlight and the cooling of the Earth's surface severely disrupted photosynthesis, the process by which plants and phytoplankton convert sunlight into energy. With photosynthesis hindered, plants and phytoplankton, the primary producers in both terrestrial and marine ecosystems, began to die off. This collapse of primary production led to a breakdown in food chains, as herbivorous dinosaurs and other plant-eating animals lost their food sources. The scarcity of plant life also affected carnivores that depended on herbivores for food, creating a cascading effect throughout the food web. The prolonged darkness and cooling also impacted the Earth's climate. The dust and aerosols in the atmosphere caused significant climatic shifts, leading to colder and more unstable weather patterns. This further stressed ecosystems already struggling with the loss of sunlight and declining temperatures. In addition to blocking sunlight, the dust cloud contributed to acid rain by providing surfaces for chemical reactions in the atmosphere. The sulfur compounds released by the impact combined with water vapor to form sulfuric acid aerosols, which then precipitated as acid rain. This rain further damaged plant life and altered the chemistry of soils and water bodies, exacerbating the environmental crisis. Evidence for this period of darkness and cooling comes from various geological records. Sediment layers from the time of the impact contain high concentrations of iridium, a rare element associated with asteroids, as well as soot and other markers of global wildfires. These layers also show signs of rapid cooling and changes in vegetation, consistent with the impact winter hypothesis. The asteroid impact that created the Chicxulub crater led to a catastrophic collapse of the food chain, which played a central role in the mass extinction event 66 million years ago. This collapse was driven by a combination of immediate and long-term environmental changes that disrupted the balance of ecosystems, leading to widespread starvation and extinction. The initial impact generated a series of devastating events, including massive tsunamis, wildfires, and a global dust cloud that blocked sunlight. This impact winter caused a dramatic drop in temperatures and prolonged darkness, severely disrupting photosynthesis, the primary process by which plants and phytoplankton convert sunlight into energy. As photosynthesis ground to a halt, plants and phytoplankton, which form the base of the food chain, began to die off. In terrestrial ecosystems, this loss of plant life meant that herbivorous dinosaurs and other plant-eating animals suddenly found their primary food sources disappearing. With vegetation scarce, herbivores experienced rapid declines in population, leading to starvation and death. The collapse of plant life also affected omnivores and carnivores. Without herbivores to prey on, carnivorous dinosaurs and other meat-eating animals faced a significant reduction in their food supply. This created a cascading effect throughout the food web as predators found themselves without adequate prey. Many carnivores, unable to find enough food, also succumbed to starvation. In marine environments, the situation was equally dire. Phytoplankton, the primary producers in ocean ecosystems, was severely impacted by the loss of sunlight. As phytoplankton populations plummeted, zooplankton and other small marine organisms that fed on them also declined. This disruption at the base of the marine food chain affected larger marine animals, including fish, marine reptiles, and other sea creatures, leading to widespread die-offs. The combination of these effects created an environment where survival became exceedingly difficult for many species. The rapid and severe loss of primary producers and the subsequent breakdown of food chains meant that ecosystems could not support the diverse array of life that had thrived before the impact. The scarcity of food and the inhospitable environmental conditions led to the extinction of approximately 75% of Earth's species, including all non-avian dinosaurs. Geological evidence supports this collapse of the food chain. Fossil records show a sudden and widespread decline in biodiversity, with many species disappearing abruptly from the fossil record at the KPG boundary. The presence of iridium-rich layers and soot in these sedimentary deposits corroborates the timing and severity of the environmental changes caused by the Chicxulub impact. The Chicxulub asteroid impact not only devastated terrestrial ecosystems, but also triggered a mass extinction of marine life. The impact's consequences profoundly disrupted marine environments, leading to the extinction of numerous marine species and drastically altering oceanic ecosystems. One of the immediate effects of the impact was the generation of massive tsunamis. These colossal waves, radiating from the impact site, traveled across the oceans, causing widespread destruction to coastal and shallow marine habitats. Coral reefs, mangroves, and seagrass beds were severely damaged or obliterated, leading to the loss of crucial habitats for many marine species. The impact also injected vast amounts of debris, including sulfuric aerosols and vaporized rock, into the atmosphere. As this material settled back into the oceans, it caused significant chemical changes. The release of sulfur compounds led to the formation of acid rain, which, upon falling into the oceans, caused a sharp drop in pH levels. This acidification had a detrimental effect on marine organisms, particularly those with calcium carbonate shells or skeletons, such as mollusks, corals, and some plankton species. Acidic conditions made it difficult for these organisms to maintain their shells, leading to a decline in their populations. The global dust cloud created by the impact blocked sunlight, leading to a dramatic reduction in photosynthesis. This impact winter affected phytoplankton, the primary producers in marine ecosystems. With phytoplankton populations plummeting, the entire marine food web was disrupted. Zooplankton, which feed on phytoplankton, experienced population declines, which in turn affected fish and other marine animals that relied on zooplankton as a food source. The loss of phytoplankton had far-reaching consequences. Phytoplankton are not only a vital food source, but also play a crucial role in carbon cycling and oxygen production in the oceans. Their decline led to a reduction in oxygen levels in marine environments, creating hypoxic conditions or dead zones, where many marine organisms could not survive. Additionally, the impact caused significant temperature fluctuations in the oceans. The initial cooling from the impact winter was followed by a period of global warming due to the release of greenhouse gases from wildfires and vaporized rock. These rapid temperature changes stressed marine species, particularly those adapted to stable environmental conditions. Fossil evidence from marine sediments around the KPG boundary shows a clear pattern of extinction. Many marine species, including ammonites, belemnites, and various planktonic foraminifera, vanished from the fossil record. The extinction of these species indicates a severe and sudden disruption of marine ecosystems. The asteroid impact that created the Chicxulub crater triggered not only immediate catastrophic events, but also long-term climate changes that significantly contributed to the mass extinction event 66 million years ago. These changes, driven by a combination of atmospheric, geological, and biological processes, created an inhospitable environment for many species, leading to widespread extinction. One of the primary drivers of long-term climate change, following the impact, was the injection of vast amounts of dust, soot, and aerosols into the atmosphere. This material formed a global cloud that blocked sunlight, leading to a dramatic cooling of the Earth's surface, a phenomenon known as impact winter. The reduced sunlight caused temperatures to plummet, disrupting photosynthesis and leading to the collapse of food chains. The cooling period, however, was not the only climatic shift. The impact also released large quantities of sulfur dioxide into the atmosphere, which, when combined with water vapor, formed sulfuric acid aerosols. These aerosols caused acid rain, further damaging vegetation and acidifying water bodies. The acid rain and cooling created highly stressful conditions for both terrestrial and marine life. As the dust and aerosols settled, the Earth's climate began to warm again, but this recovery was complicated by the release of greenhouse gases. The impact and subsequent wildfires released significant amounts of carbon dioxide, CO2, and methane (CH4) into the atmosphere. These gases trapped heat, leading to a period of global warming that followed the initial cooling. This rapid warming further stressed ecosystems already weakened by the impact winter. The long-term climate changes also affected ocean circulation patterns. The cooling and then warming of the Earth's surface altered the temperature gradients between the equator and the poles, which in turn affected ocean currents. These changes disrupted nutrient distribution in the oceans, impacting marine life that depended on these nutrients for survival. The combined effects of cooling, acid rain, and subsequent warming created an unstable and fluctuating climate. Many species, unable to adapt to these rapid and extreme changes, faced extinction. The long-term climate changes led to shifts in habitats, forcing species to migrate, adapt, or perish. For example, forests that once thrived in certain regions could no longer sustain themselves, leading to the loss of habitats for numerous species. Geological records from the period show evidence of these climatic shifts. Sediment cores reveal layers of iridium, a marker of the asteroid impact, followed by layers rich in soot and sulfur compounds. These layers correspond to periods of cooling and acid rain, followed by evidence of increased carbon dioxide levels, indicating global warming. The KT boundary, also known as the Cretaceous Paleogene (KPG) boundary, marks a significant geological and biological transition in Earth's history approximately 66 million years ago. This boundary represents the point in time when a mass extinction event wiped out about 75% of Earth's species, including all non-avian dinosaurs. The KT boundary is characterized by a distinct layer of sediment found worldwide, providing crucial evidence of the catastrophic events that led to the mass extinction. One of the most notable features of the KT boundary is a thin layer of clay enriched with iridium, a rare element more common in asteroids than in the Earth's crust. This iridium anomaly was first discovered in the 1980s by Lewis and Walter Alvarez, leading to the hypothesis that an asteroid impact was responsible for the mass extinction. The global presence of this iridium layer suggests that the impact had worldwide effects. The KT boundary layer also contains other evidence of the catastrophic impact, including shocked quartz and microtectites. Shocked quartz forms under the extreme pressures and temperatures associated with impact events, while microtectites are small glassy particles created by the melting and rapid cooling of rocks during the impact. These materials provide further confirmation of the immense energy released by the Chicxulub impact. In addition to these geological markers, the KT boundary is characterized by a sudden and dramatic change in the fossil record. Below the boundary, fossils show a rich diversity of dinosaurs, ammonites, and other species that thrived during the Cretaceous period. Above the boundary, these species abruptly disappear, replaced by a less diverse assemblage of organisms that survived the extinction event. This shift in the fossil record highlights the sudden and widespread nature of the extinction. The environmental changes caused by the asteroid impact and documented in the KT boundary had far-reaching effects on Earth's ecosystems. The impact triggered massive wildfires, tsunamis, acid rain, and an impact winter, leading to prolonged darkness and cooling. These events caused the collapse of food chains and created inhospitable conditions for many species. The KT boundary layer has been found in various locations around the world, from deep-sea sediment cores to continental rocks. This widespread distribution underscores the global reach of the impact's effects. Studying the KT boundary has provided scientists with valuable insights into the processes and consequences of mass extinction events. Fossil evidence provides a crucial window into the catastrophic events and mass extinction at the end of the Cretaceous period, approximately 66 million years ago. The fossil record before and after the KT boundary reveals a stark contrast in the diversity and abundance of life, offering insights into the impact of the Chicxulub asteroid on Earth's ecosystems. Before the KT boundary, the fossil record shows a rich and diverse array of life forms. Dinosaurs, the dominant terrestrial vertebrates, included iconic species such as Tyrannosaurus rex, Triceratops, and Velociraptor. In the oceans, large marine reptiles like mosasaurs and plesiosaurs thrived alongside ammonites, a group of spiral-shelled cephalopods. Flowering plants, insects, and small mammals were also abundant, indicating complex and vibrant ecosystems. The KT boundary itself is marked by a distinct layer of sediment that contains high levels of iridium, a rare element on Earth but common in asteroids. This iridium anomaly, discovered by Lewis and Walter Alvarez in the 1980s, supports the hypothesis that an asteroid impact was responsible for the mass extinction. This boundary layer also contains shocked quartz and microtectites, providing further evidence of a massive impact event. Above the KT boundary, the fossil record shows a dramatic reduction in the diversity and abundance of life. The non-avian dinosaurs, which had dominated terrestrial ecosystems for over 160 million years, disappear abruptly from the fossil record. Similarly, marine reptiles like mosasaurs and plesiosaurs, as well as ammonites, are no longer found. This sudden loss of major groups of organisms indicates a rapid and catastrophic event. The post-boundary fossil record reveals a world struggling to recover from the devastation. Early Paleogene fossils show a much simpler and less diverse array of life forms. Mammals, which had been relatively small and inconspicuous during the age of dinosaurs, began to diversify and occupy ecological niches left vacant by the extinction. Birds, the only surviving lineage of dinosaurs, also started to radiate and evolve into various forms. Plant fossils provide additional evidence of the catastrophic changes. The diversity of flowering plants, which had flourished during the Cretaceous, shows a significant decline. Fern spores are abundant in the immediate aftermath of the boundary, suggesting that ferns, which can quickly colonize disturbed environments, temporarily dominated the landscape before other plants recovered. Fossilized pollen and spores also indicate changes in vegetation. A sharp decline in the variety of pollen types corresponds to the immediate post-impact period, reflecting the collapse of complex plant communities. Over time, new plant species emerged and spread, leading to the gradual recovery of forests and other ecosystems. The mass extinction event caused by the Chicxulub asteroid impact 66 million years ago marked the end of the Cretaceous period and led to the extinction of approximately 75% of Earth's species, including all non-avian dinosaurs. However, some species survived the cataclysmic event and went on to evolve and diversify in the aftermath. The survival and subsequent evolution of these species reshaped Earth's ecosystems and paved the way for the rise of mammals and birds. Among the most notable survivors were the avian dinosaurs, or birds. Unlike their non-avian relatives, birds managed to survive the impact and its aftermath. Their ability to fly, small size, and diverse diets likely contributed to their survival. The evolutionary adaptability of birds allowed them to exploit new ecological niches left vacant by the extinction of other species. Over time, birds diversified into the myriad forms we see today, from small songbirds to large predators like eagles. Mammals also survived the mass extinction and rapidly diversified in the new predator-free environment. Before the impact, mammals were generally small, nocturnal, and occupied minor ecological niches. With the extinction of the dominant dinosaurs, mammals began to evolve and occupy a wider range of ecological roles. This adaptive radiation led to the emergence of various mammalian groups, including primates, ungulates, and carnivores. The success of mammals in the post-impact world set the stage for the eventual rise of humans. Certain amphibians and reptiles also survived the extinction event. Crocodiles and turtles, for example, managed to endure the harsh post-impact conditions. These species likely survived due to their ability to live in aquatic environments, which may have provided some insulation from the immediate effects of the impact, such as wildfires and acid rain. Their survival allowed them to continue evolving and diversifying in the new ecosystems. In the oceans, some fish and marine invertebrates managed to survive the mass extinction. While many marine species, including the ammonites and large marine reptiles, went extinct, others adapted to the changing conditions. Fish and other marine life that could exploit different food sources or adapt to altered habitats found new opportunities to thrive. The survival of these species helped maintain marine ecosystems and allowed for the eventual recovery of marine biodiversity. Plant life also experienced a significant upheaval, but certain species were able to survive and adapt. Ferns, which can quickly colonize disturbed areas, became dominant in the immediate aftermath of the impact. Over time, flowering plants and other vegetation began to recover and diversify. Insects, closely tied to plant life, also managed to survive and adapt. The recovery of plant-insect interactions played a crucial role in the re-establishment of terrestrial ecosystems. The mass extinction event created opportunities for evolutionary innovations. With many ecological niches left vacant, surviving species underwent adaptive radiations, leading to the development of new traits and behaviors. This period of evolutionary experimentation resulted in the emergence of novel forms and functions, shaping the future trajectory of life on Earth. Impact craters are powerful reminders of the dynamic and sometimes violent nature of our planet and the solar system. The Chicxulub crater, associated with the mass extinction event that ended the Cretaceous period, is one of the most famous examples, but it is far from the only significant impact site on Earth. Modern-day impact craters offer valuable insights into the history of asteroid impacts and their effects on the planet, as well as the potential threats posed by future impacts. Located in Arizona, this well-preserved crater is about 1.2 kilometers in diameter and 170 meters deep. It was formed approximately 50,000 years ago by an iron-nickel asteroid, about 50 meters wide. The Barringer crater is a prime example of a relatively recent and small impact event. At approximately 300 kilometers in diameter, Vredefort is one of the largest known impact structures on Earth. It was created around 2 billion years ago by an asteroid estimated to be about 10–15 kilometers in diameter. The immense energy released by the impact created a multi-ringed structure visible even today. Formed about 1.85 billion years ago, the Sudbury Basin in Ontario is another massive impact site, approximately 130 kilometers in diameter. The impact that created this basin was likely caused by an asteroid about 10 kilometers wide. The Sudbury Basin is also notable for its rich deposits of nickel, copper, and other metals, making it a significant mining region. This well-preserved impact structure in Quebec is about 100 kilometers in diameter and was formed around 214 million years ago. The crater's distinctive ring-shaped lake, Lac Manicouagan, makes it easily recognizable from space. Buried beneath the Chesapeake Bay, this crater is approximately 85 kilometers in diameter and was formed about 35 million years ago. The impact significantly influenced the geology and hydrology of the region, affecting the modern Chesapeake Bay's shape and water flow. Studying modern-day impact craters provides critical insights into Earth's geological history and the processes that shape planetary surfaces. These craters reveal information about the frequency and scale of past impact events, contributing to our understanding of the potential risks posed by near-Earth objects, NEOs. Analyzing the mineralogy and shock features in impact craters helps scientists understand the conditions and effects of high-energy collisions. While the Chicxulub impact is infamous for causing mass extinction, smaller impacts also have significant ecological and environmental consequences. For example, the Tunguska event in 1908, which flattened a vast area of Siberian forest, demonstrated the destructive potential of relatively small asteroids. Studying these events helps scientists assess the potential impacts on modern human society and develop mitigation strategies. The study of impact craters emphasizes the importance of monitoring NEOs and developing strategies to mitigate potential threats. Organizations like NASA's Planetary Defense Coordination Office and international partners work to detect, track, and characterize NEOs. Efforts to develop deflection techniques, such as the DART, Double Asteroid Redirection Test, mission, aim to prevent potential future impacts. The Alvarez hypothesis, proposed by father-son duo Luis and Walter Alvarez in 1980, revolutionized our understanding of the mass extinction event that occurred approximately 66 million years ago, marking the end of the Cretaceous period. This hypothesis posits that a massive asteroid impact was the primary cause of the mass extinction that wiped out about 75% of Earth's species, including all non-avian dinosaurs. Luis Alvarez, a Nobel Prize-winning physicist, and his geologist son, Walter, were studying the KT boundary layer, a distinct layer of sediment found worldwide that marks the transition from the Cretaceous to the Paleogene period. They discovered that this boundary layer was unusually rich in iridium, a rare element on Earth, but abundant in asteroids and comets. This discovery led them to propose that an extraterrestrial object, such as an asteroid, struck the Earth, creating the iridium anomaly observed in the boundary layer. The worldwide presence of high iridium concentrations at the KT boundary was a critical piece of evidence. Iridium is rare in the Earth's crust but common in asteroids, supporting the idea of an extraterrestrial impact. Another supporting piece of evidence was the presence of shocked quartz in the boundary layer. Shocked quartz forms under high-pressure conditions, typically associated with impact events, further corroborating the impact hypothesis. The discovery of microtectites, small glassy particles formed by the melting and rapid cooling of rocks during an impact, provided additional support. These particles were found in the KT boundary layer, indicating the presence of an impact. The identification of the Chicxulub crater on the Yucatan Peninsula in Mexico provided a specific impact site. The crater's size and age matched the proposed timing of the mass extinction, making it a likely candidate for the impact event described by the Alvarez hypothesis. The Alvarez hypothesis significantly advanced our understanding of mass extinction events. It shifted the scientific consensus from gradualistic models of extinction, which emphasized slow, progressive changes, to recognizing the potential for sudden, catastrophic events to drive mass extinctions. This hypothesis also spurred extensive research into other potential impact events in Earth's history, and their role in shaping the planet's biological and geological evolution. Initially, the hypothesis faced skepticism and controversy within the scientific community. Critics argued that the evidence was insufficient and that other factors, such as volcanic activity, could have contributed to the extinction. Over time, however, accumulating evidence from various scientific fields, including geology, paleontology, and geochemistry, strengthened the case for the impact hypothesis. The Alvarez hypothesis has broader implications beyond the specific mass extinction event it describes. It highlights the potential for extraterrestrial objects to influence life on Earth and underscores the importance of monitoring near-Earth objects, NEOs, for potential future impacts. This understanding has led to the development of planetary defense initiatives aimed at detecting and mitigating the threat of asteroid impacts. The geological timeline surrounding the Cretaceous-Paleogene (KPG) boundary provides critical context for understanding the mass extinction event that wiped out approximately 75% of Earth's species, including all non-avian dinosaurs. This timeline highlights the sequence of events before, during, and after the asteroid impact that formed the Chicxulub crater. During the late Cretaceous period, Earth was dominated by a warm climate, high sea levels, and diverse ecosystems. Dinosaurs were the dominant terrestrial vertebrates, thriving in various habitats across the planet. Marine ecosystems were equally rich, with large marine reptiles, ammonites, and diverse plankton populations. The KPG boundary marks the transition from the Cretaceous to the Paleogene period and is characterized by a distinct layer of sediment found worldwide. This boundary is significant because it coincides with the mass extinction event and provides evidence of the catastrophic asteroid impact. Approximately 66 million years ago, a massive asteroid, estimated to be about 10–15 kilometers in diameter, struck the Yucatan Peninsula in present-day Mexico. The impact created the Chicxulub crater, releasing energy equivalent to billions of atomic bombs. The impact generated a series of catastrophic events, including massive tsunamis, wildfires, and the injection of vast amounts of dust and aerosols into the atmosphere. This led to a dramatic drop in temperatures, known as AN, and caused prolonged darkness that severely disrupted photosynthesis. The period following the impact was marked by significant climatic and ecological changes that shaped the evolution of life on Earth. The immediate aftermath of the impact was characterized by a sudden and severe cooling of the Earth's surface due to the blocking of sunlight by dust and aerosols. This impact winter led to the collapse of food chains as plants and phytoplankton, the primary producers, died off. The thermal radiation from the impact ignited widespread wildfires, further contributing to the environmental stress by releasing additional aerosols and greenhouse gases into the atmosphere. The impact released sulfuric aerosols, leading to acid rain that acidified soils and water bodies, harming plant and aquatic life. Ocean acidification particularly affected marine organisms with calcium carbonate shells or skeletons, such as corals and certain plankton species. Following the initial cooling, the Earth experienced a period of global warming due to the release of CO2 and other greenhouse gases from the impact and subsequent wildfires. These rapid climate fluctuations further stressed surviving species and ecosystems. In the millions of years Following the impact, Earth's ecosystems gradually recovered and diversified. The extinction of the dominant dinosaurs allowed mammals and birds to occupy new ecological niches. This period, known as the Paleogene, saw the rise of mammals as the dominant terrestrial vertebrates and the diversification of birds and flowering plants. With the extinction of large dinosaurs, mammals evolved and diversified, leading to the emergence of various groups, including primates, ungulates, and carnivores. Birds, the only surviving lineage of dinosaurs, also diversified, adapting to various ecological niches and giving rise to the wide variety of avian species we see today. Plant life gradually recovered, with flowering plants becoming increasingly dominant. This recovery was crucial for the re-establishment of terrestrial ecosystems and the support of diverse animal life. While the asteroid impact hypothesis is the most widely accepted explanation for the mass extinction event that wiped out the dinosaurs, several other theories have been proposed over the years. These theories suggest alternative or complementary factors that may have contributed to the extinction at the end of the Cretaceous period. One prominent theory posits that massive volcanic eruptions, specifically those in the Deccan Traps in present-day India, played a significant role in the extinction event. These eruptions, occurring around the same time as the Chicxulub impact, would have released vast amounts of volcanic gases, including sulfur dioxide, SO, and carbon dioxide, CO2, into the atmosphere. The release of SO2 would have led to the formation of sulfuric acid aerosols in the atmosphere, causing acid rain. This acid rain could have severely damaged vegetation, acidified water bodies, and disrupted ecosystems. The volcanic aerosols would have blocked sunlight, causing short-term global cooling similar to the impact winter proposed by the asteroid hypothesis. Additionally, the release of CO2 would have contributed to long-term global warming, leading to climatic instability that stressed ecosystems. Gradual climate change over millions of years has also been suggested as a contributing factor to the mass extinction. Shifts in global temperatures, sea levels, and atmospheric composition could have gradually altered habitats and stressed species, making them more vulnerable to sudden catastrophic events like the asteroid impact. Fluctuations in sea levels during the late Cretaceous period could have caused habitat loss for coastal and marine species. These changes would have affected marine ecosystems and food chains, leading to increased competition and extinction pressures. Variations in global temperatures could have affected the distribution of plant and animal species. Cooler temperatures may have led to reduced plant growth, impacting herbivorous dinosaurs and the carnivores that preyed on them. Another theory suggests that widespread disease could have contributed to the extinction of the dinosaurs. Epidemic diseases may have spread rapidly among dinosaur populations, weakening them and making them more susceptible to other environmental stresses. The spread of new or existing pathogens could have caused high mortality rates among dinosaur populations. This theory is supported by the observation that disease can have devastating effects on animal populations, particularly when they lack immunity. Disease could have interacted with other extinction drivers, such as climate change or environmental stress from volcanic activity, compounding the effects and leading to a higher overall extinction rate. Many scientists believe that the mass extinction was likely the result of a combination of factors rather than a single cause. The asteroid impact, volcanic activity, climate change, and other environmental stresses may have collectively contributed to the extinction event. The combined effects of an asteroid impact, volcanic eruptions, and climate change could have created a perfect storm of environmental challenges. The interaction of these factors would have increased the severity and duration of the extinction event. Different species would have had varying levels of resilience to these factors. Those unable to adapt to the rapidly changing conditions would have been more likely to go extinct, while others may have survived and adapted. Asteroid impact simulations are essential tools for understanding the dynamics and consequences of extraterrestrial collisions with Earth. These simulations use advanced computer models to recreate the physical processes that occur during an impact event, providing valuable insights into the effects on the environment, climate, and life. By studying these simulations, scientists can better understand past events like the Chicxulub impact and prepare for potential future threats. Asteroid impact simulations involve complex calculations that account for various factors, including the size, speed, and composition of the asteroid, as well as the angle of impact and the characteristics of the impact site. These simulations use physics-based models to predict the behavior of the asteroid and the Earth's materials during the collision. The simulations calculate the energy released upon impact, equivalent to billions of atomic bombs, to determine the extent of shock waves, heat, and pressure generated. The models simulate the formation of the impact crater, including the excavation of materials, the creation of central peaks, and the collapse of crater walls. The size and shape of the crater provide insights into the magnitude of the event. Simulations track the distribution of ejecta, including debris, dust, and aerosols, thrown into the atmosphere. Understanding the dispersal patterns helps predict the global effects on climate and environment. Asteroid impact simulations help scientists understand the immediate and long-term environmental consequences of such events. By modeling the amount of dust and aerosols injected into the atmosphere, simulations predict the reduction in sunlight reaching the Earth's surface. This leads to a dramatic cooling effect known as impact winter, which disrupts photosynthesis and food chains. Simulations of the heat generated by the impact show how it could ignite widespread wildfires, contributing to atmospheric soot and further cooling the planet. By modeling the displacement of water from oceanic impacts, simulations predict the generation and propagation of massive tsunamis. These waves can inundate coastal areas and cause significant destruction far from the impact site. Understanding the biological and climatic effects of asteroid impacts is crucial for assessing the risks to life on Earth. Simulations help explain how the combined effects of cooling, darkness, wildfires, and acid rain could lead to mass extinctions. By recreating these conditions, scientists can study the vulnerabilities of different species and ecosystems. 2. Climate change, the long-term climatic effects, including global warming from greenhouse gas release, are modeled to understand the overall impact on Earth's climate systems. Asteroid impact simulations are not just tools for studying past events. They are also vital for preparing for potential future impacts. Simulations of various impact scenarios help assess the potential risks posed by near-Earth objects. NEOS. By understanding the likely consequences, scientists can prioritize monitoring efforts and develop mitigation strategies. Simulations are used to test the effectiveness of asteroid deflection techniques, such as kinetic impactors or nuclear explosions. These models help refine methods for altering an asteroid's trajectory to prevent a collision with Earth. By predicting the possible outcomes of an impact, simulations inform emergency response plans. Governments and organizations can use this information to prepare for potential evacuations, resource allocation, and recovery efforts. The asteroid impact that caused the extinction of the dinosaurs, approximately 66 million years ago, offers profound lessons for humanity. Understanding this catastrophic event helps us grasp the potential threats posed by similar extraterrestrial objects and the importance of preparing for such eventualities. By studying the past, we can develop strategies to mitigate future risks and enhance our resilience against natural disasters. One of the key lessons from the Chicxulub impact is the necessity of monitoring near-Earth objects, NEOS. These are asteroids and comets that have orbits that bring them close to Earth's orbit. Tracking NEOS is crucial for early detection of potential collision threats. Advanced telescopes and space missions are employed to detect and track NEOS. Projects like ENASA's Near-Earth Object Observations (NEOO) program aim to identify and catalog these objects, assessing their sizes, trajectories, and potential impact risks. Accurate prediction models are essential to determine the likelihood of an impact and its potential consequences. By understanding an NEO's orbit, scientists can predict future close approaches and possible collisions with Earth. In addition to monitoring, developing effective strategies to deflect or mitigate the impact of a potential collision is vital. One proposed method involves sending a spacecraft to collide with an asteroid, altering its trajectory. The DART, Double Asteroid Redirection Test, mission is an example of this approach, aiming to test the feasibility of such deflection techniques. Another strategy involves using nuclear explosions near the asteroid to change its course. While more controversial due to the risks involved, this method could be effective for larger objects. The global nature of the threat posed by NEOS necessitates international collaboration and comprehensive preparedness plans. Organizations like the United Nations have recognized the importance of international cooperation in addressing the threat of asteroid impacts. Collaborative efforts ensure that resources, knowledge, and technologies are shared to enhance global readiness. Developing detailed emergency response plans is crucial for minimizing the impact of an asteroid collision. These plans should include evacuation procedures, resource distribution, and recovery strategies to protect human lives and infrastructure. Raising public awareness about the risks and potential impacts of asteroid collisions is essential for gaining support for monitoring and mitigation efforts. Informing the public through educational campaigns can help people understand the importance of NEO monitoring and the steps being taken to protect the planet. Public support is vital for funding and sustaining these initiatives. Conducting simulations and drills can prepare communities for potential impact scenarios. These exercises help identify weaknesses in preparedness plans and ensure that people know how to respond in an emergency. Studying the Chicxulub impact and other historical asteroid events provides valuable insights into the potential consequences of future impacts. Ongoing research into past impacts helps scientists understand the environmental and biological effects of such events. This knowledge is crucial for predicting and mitigating the impacts of future collisions. Advances in technology, driven by the need to monitor and mitigate asteroid impacts, have broader applications. Innovations in space exploration, data analysis, and emergency response can benefit other areas of science and public